good afternoon, and welcome to my talk on the impacts of wind speed and temperature on tornado severity in South Carolina. So, first things first, here's our problem. South Carolina is ranked with the 19th highest increase in tornado frequency nationally. This is right up there with states like Oklahoma and Texas, you know, Twisterland, Tornado Alley. Right up there with them, and we are 19th. That's not a small number. Due to noted terrible regional disparities, there is little to no data on lead times and factors, including the state of South Carolina, essentially meaning that, not to mention we don't know what exactly is happening with the lack of warning for tornadoes, but we also have very little literature regarding the state of South Carolina, period. So we have nothing to work with. So without further ado, here's the purpose and hypothesis of my study. The purpose was to determine if change in wind speed and temperature would be accurate predictors of tornado severity in the state of South Carolina, specifically the Midlands, and I'll show you the highlighted region in a minute. And then finally, the hypothesis was that a change in wind speed and or temperature at 15-minute intervals before tornado touchdown can be indicative of tornado severity. So, moving right along. This is stage one of my methodology, and as you can see, I talked about, oh, that is not, oh no it is, aha! So, this is the region that we looked into for South Carolina. This is also known as the Midlands region. So, Spartanburg, unfortunately, was not included. Sorry y'all, love you, mean it. But, this included everywhere from Orangeburg upward into Lawrence, so close. So, from this region, we gathered data from a National Weather Service database that had a confirmed list of tornadoes that touched down in that Midlands area. We limited the severities that we were looking into from EF0 to EF2, and this is on the enhanced Fujita scale that measures tornado severity. And we also only looked at the years of 2015 to 2018. So from that, we then looked at wind speed and temperature data from the Iowa Mesonet service. As you can see in this graphic, we have stations all over the state. So from this region, we looked at those stations and gathered wind speed and temperature data at 15-minute increments close to a tornado touchdown event. So say, for instance, there's a tornado about right here. We would look at this station right here and gather wind speed and temperature data at 15-minute increments before touchdown. So we have two graphs for that. We have about from 45 to 15 minutes before touchdown, and then change wind speed from 30 to 15 minutes. So, and this is again, like I said, based on weather station closest to tornado touchdown. Then we're on to methodology stage 2. So we referred back again to our lovely National Weather Service database for a list of all recorded thunderstorms from a weather station from 2015 to 2018. So, for sake of time, I limited it to one station, which you can see in this lovely polygon here is the Aiken station. Totally not biased, because that's definitely not my hometown. But it was a good starting point. So, from that station, we gathered all thunderstorm data from 2015 to 2018, and gathered wind speeds at each 15-minute period during the duration of each thunderstorm event, and plotted the frequency of wind speed changes, as well as the probability of false alarm. And we did that using the number of periods that would predict a tornado, minus the number of confirmed tornadoes and that wind speed drop, over, of course, the number of periods that would predict a tornado, to get our lovely PFA value. Now for the fun of graphs. So, we have our average wind speed graphs. So this right here is the 30 to 15 minute average change in wind speed. Your y-axis is your different severities. So as you see, we have EF2 right here, EF1, and of course EF0. So, as you can see, change in wind speed tends to be negative right before tornado touchdown for EF2s, stay roughly the same for EF1s, so fairly constant, and then spike dramatically right before EF0. Well, I say dramatically. It looks kind of dramatic on this graph, but numbers are rather small. But I also have the R-squared value and the p-value up here. As you can see, this definitely does have a correlation with a R-squared value of 0.99, p-value of 0.051, which is, okay. And then, for our 45 to 15 minute graph, we have a bit more of a strong correlation, but not as much dramatic change as we saw in the 30 to 15 minute graph. So the wind speed in the 45 to 15 minutes before tornado touchdown, you can see that wind speed is still dropping before an EF2 tornado and still staying constant EF1, and then going up a little bit before EF0. And then, of course, the lovely R-squared and p-values are right up here. But at the end of the day, what I want to show in this slide is that there is a correlation shown between change in wind speed and tornado severity. Now, as to what we can do with that, that will be something for future study, but it's something to observe now. Now for temperature. Temperature was a heartbreaker. There was absolutely no correlation shown between change in temperature and tornado severity, at least what we could find. That R-squared value is, well, it's interesting. Kind of sad, but it is what it is. And also, forgot to mention this on the previous slide, wind speed is in miles per hour. Temperature for this is in Celsius. I know that sounds mixed. This is National Weather Service and FEMA we're dealing with here. We don't like to stay constant. So, same setup as last time, tornado severity, and then, of course, your drops. And again, no correlation with this slide. Now, we decided to abandon the temperature correlation because, well, there wasn't any. So in order to look at our prediction graphs or frequency modules, we decided to look at change in wind speed. So what we did was we looked at the frequency of change in wind speed for all of the thunderstorm events in that area. And for the sake of our prediction of false alarm value, we capped it at about plus or minus 4 miles per hour. So this little spot right here. And that was about 93 events in this spot here of wind speed changes. So from those 93 events of wind speed changes, there were 4 tornadoes. So our prediction value is about 96% of false positive, which is not fantastic, but good news, kind of. The current National Weather Service average of false alarms rate is about 70%. So they're not really doing fantastic either. So we're doing decent. And now, wrapping it up with some conclusions and next steps. So one of the conclusions we had is that change in wind speed definitely has a correlation with tornado occurrence and severity. And then change temperature clearly does not. So we abandoned that one real fast. And then probability of false alarm using a change in wind speed that we did was about roughly 96%. And then some next steps to continue this research. I want to analyze thunderstorm data for the remaining Midland stations since I only did, well, my hometown. Should probably branch out a little bit more. And also, wouldn't hurt to look at the rest of South Carolina tornado sites as well and throw those in there because I imagine Spartanburg's feeling just a little bit left out. Also, I'd like to determine if change in, say, barometric pressure or dew point could be indicators of tornadoes as well, because in weather, everything interacts with each other. So, you know, if change in wind speed does something, maybe dew point, maybe pressure, maybe something else. Just anything at this point. Also, we only looked at change in wind speed and temperature, and there could be a point made that instantaneous wind speed and temperature, so wind speed right at the moment of a tornado touchdown could be something. That also goes for barometric pressure or dew point as well. But that requires a whole other study. Obviously not enough time for this year. And then lastly, in order to do any of this, we need some technological improvements to measuring equipment, because the best that we had were 15-minute increments of stored data. And that is really pitiful if you're looking at a tornado that happens in about a minute or so. So we really need something better than that. And to put it to you this way, when I was looking for another option, when 15 minutes wasn't good enough, the next best option was an hour increment. And that would tell me nothing. And that was also National Weather Service. So we definitely need to do better in that area. Now finally, our acknowledgements. So first one I'd like to acknowledge is Paul Matthews down at Aiken County Emergency Management. He was involved in my early research with this, with the RC Winds program, which is exactly like the Iowa Mesonet service. It's just not as active as Iowa Mesonet is right now. We don't have as many stations, and they're not running, so there's that. Also, Savannah River National Laboratory, Atmospheric Technologies Lab, Dr. Steve Weinbeck. He will be my mentor over the summer, and he guided me to some other resources to consider for this research project. And finally, Dr. John Quagliario from National Weather Service in Columbia. He guided me to the Iowa Mesonet service, and I was originally going to have an hour time blocks. He was the one that got me to 15 minutes, so he made this possible. And lastly, but certainly not least, Dr. John MacCarthy in the Wofford Physics Department. If it wasn't for him, this wouldn't have happened. So. Now, does anyone have any questions? Yes.
Do you remember how many tornadoes of each type there were, like EF2s, EF1s, EF0s, and that?
I could not give you an exact number, but I could tell you that EF1s are far more common than EF0s and EF2s. So I'd say out of those four, probably 3 were EF1s. But actually, probably 2. That'd be more accurate, because then we'd have one for EF0 and one for EF2. That'd be a bit more accurate. But also, as times are changing, we are starting to have EF3 tornadoes as well, and that's not been a data point until recently. If you've heard of the Allendale tornado, that was a big deal. So now we're going to have to consider EF3s. So that's another thing. Yes?
Can you explain the difference between EF0, EF1, and EF2? I'm not exactly sure.
I'm glad you asked. I have a slide. So this is the enhanced Fujita scale. And so we generally use 2 scales in meteorology. Enhanced Fujita is based on first the old school Fujita scale, so we'll start with this first. This is based more on damage. So you estimate your wind speeds based on the amount of damage you have. So in EF0, you'd have some light damage, maybe some trees falling, shingles off roofs, etc. EF1 will have some, or F1, not EF yet. F1 will have some roof surfaces peeled off, mobile homes are pushed, all that fun stuff. And F2 is considerable damage. In one of my studies, I actually found a damage report for about, what was it, 4,000 turkeys killed by an EF2. That was in Union County, I believe. It was interesting report. No mention about the barn, but a lot of turkeys. So believe it or not, they use whatever data information they can find to estimate a wind speed. Now, EF, which is what we used, they go by wind gust. So this is more instantaneous wind speed, but the thing is, this is really hard. You can't measure this. You have to estimate it. So it's based on the Fujita scale of damage, and then you estimate, well, this would have been this bad at this time. So you can't really get anything at tornado site right now to say, okay, this is exactly what this wind gust was. You can estimate it based on the damage. So that's roughly what an EF scale does. We have any more questions? Yes, Blair.
I was just wondering, I know like a lot of us have heard like the calm before the storm, and so
yes.
Does that kind of like go into what your research showed, that like the wind speed actually maybe decreases the change?
Yes, actually. That is something that I thought of and I saw firsthand when I was on vacation at Beaufort. So during the Allendale tornado, I was in Beaufort, and we had some tornadoes that came through then, and lo and behold, it had the same effect of an exact complete calm before we saw a funnel. And I don't have Allendale data with me, unfortunately. I'll have to go back and get that for you. But from the Allendale tornado data that I saw shortly after it touched down, it also did the same thing. So, what do you think? Yes?
So the false positive rate's really concerning from a behavioral standpoint because you are basically in these areas. So I've lived in Alabama, the sirens go off, right? And so what happens is when they go off and no tornado comes is that you want to ignore the sirens, which are there to protect you, to tell you to go. So, so what do you do about that? It seems incredibly problematic.
Well, one of the issues that happens with that, and this is something the National Weather Service has been dealing with, is this is how they determine whether or not to sound the alarm. So this is a base velocity radar, and what they do is they look for rotation in this cell, and then that's how they issue the alarm. The thing is, tornadoes are very temperamental, so the chances of them actually forming into a funnel on the ground based on just cloud rotation alone can be very low. So there's a lot of times where they'll see on this radar, okay, this sucker is rotating, let's go ahead and get them to shelter fast, and that will give them a higher false positive rating, but it will give them their 30% true positive rating. As with my research, I think it's just we don't have all of the weather stations up and going in different parts of the area, and I think the time value is what killed us there. I think if we had a bit more of a closer time value, I think we could get a little more precise data, could probably get a better false positive rate. Any more questions from the audience?
All right, thanks everybody.